In this video, we're going to take a look at something that's called an inverse function, or a function that undoes another function. You might think about it as the control Z, undo. Undo what was done. Control CTRL Z, undo the function. Another way to think about this visually is if we've got some function machine, f of x, that's going to take a number into it. Maybe it takes a 3 in, and it comes out as a 5. The idea is there's this other function machine that is going to undo that function, and it's called f inverse of x. Notice the inverse function is written f inverse of x with the little -1. It might look like an exponent. It is not an exponent. Just like f of x does not mean f times x. It is a notation that tells us to take the inverse of the function. So if I've got this 5 that came out of f of x and we plug it into the inverse machine will take you back to where you started. So it becomes a 3. Similarly, if I take a -4 and plug it into the function machine, maybe I get a 2 out. When we plug it into the inverse, it's going to take me back to where it started. It undoes the other function, giving me out -4. Another way to think about it is just with variables. Any x you put in will come out of the function machine as some y. So when y goes into the inverse, what comes out should be x. Get back to where you started. Undoes. Control Z. Undoes the other function. And the way we know if two functions are inverses, if we've got an f of x and a g of x, we want to know if they're inverses, if one truly undoes the other. What we'll do is we'll calculate the compositions, f of g of x and g of f of x, because that's what we're doing with this double entry thing. If we go into a function and immediately that result is plugged into another function, that's a composition. When we do that, notice the x that went in came out as a y, and the inverse changed it back into an x. Whenever you go through both functions, the answer should be x if they are truly inverse functions. Not x plus 3, not the square root of x, simply x. If they are truly inverses, it should take you back to where you started. So let's test if a couple functions are inverses. We've got f of x equals 3x minus 8. G of x is x over 3 plus 8. Kind of seems like they'd be inverses, being as we've got 3 times x, and then x divided by 3. That's an opposite inverse operation. And subtracting 8 became adding 8. That's an opposite inverse operation. So hey, I feel pretty good. The way we know is we calculate the composition. We calculate f of g of x. Well, what is g of x? G of x is x over 3 plus 8. So we're calculating f of the g function, the x over 3 plus 8, which means what is inside of f is going to replace the variable in f. We're going to replace the x in 3x minus 8 with whatever's inside the function, the x over 3 plus 8. And now we simplify. We can start simplifying by distributing. That's going to give us 3x over 3 plus 24 minus 8. And then simplifying, the 3's divide out, leaving just x, plus, combine like terms, 24 minus 8 is 16. Did we end up with x like we wanted when you went from one function to the next? No. We ended up with x plus 16. That means these functions are not inverses. No, they are not inverses because they don't undo each other. They're off by 16, if you will. The only way they're inverses is if we calculate the composition and the result we get is simply x. So let's try another example. We've got f of x equals 5 over x minus 3 plus 6. G of x equals 5 over x minus 6 plus 3. Gee, they might be inverses. I see a lot of the same numbers. They both have 5 in the numerator. I don't know. That doesn't look like they're really undoing each other if they're both doing 5 divided by. How do we know? We calculate the composition, and we need to calculate both compositions. So first we'll find f of g of x, and then we will find g of f of x, and hopefully the answer for both will be x. I guess we only have to calculate one of them if it doesn't come out to x. We have to calculate both if it does. So inside we've got g of x, and we know g of x is equal to this big thing. So inside of f is g, which is 5 over x minus 6 plus 3. And that 5 over x minus 6 plus 3 then is being plugged into f for the variable. Where we see the x, we're now going to see 5 over x minus 6 plus 3. So it becomes 5 over x, which is now 5 over x minus 6 plus 3 minus 3 plus 6. And now we try and simplify. We can combine like terms. 3 minus 3 is 0. So we've got 5 over x minus 6 plus 6. To divide by a fraction means we want to multiply by the reciprocal. So we've got 5 times the reciprocal, x minus 6 over 5. Put that in parentheses. Plus 6. Well, this is nice because the 5's divide out, and we have x minus 6 plus 6, which is equal to simply x. That's what we wanted to get. There's a pretty good chance we're looking at inverses now because the composition came out to be just x. However, to know for sure, we still have to calculate the composition the other direction because inverse functions should be able to be composed in either order. So we go back to the g of f of x. And this time we're going to plug the f in. Well, what's f? This guy. So we've got g of the 5 over x minus 3 plus 6. And we'll plug all that stuff in for the x in the other function, giving us 5 over x minus 3 plus 6. And continuing with the function, we have a minus 6 plus 3. And this is going to look very similar to what we just saw before. The 6 minus 6 is 0, so we have 5 over x minus 3 plus 3. Again, division we know means we multiply by the reciprocal. 5 times x minus 3 over 5 plus 3. The 5's divide out. We have x minus 3 plus 3, which, when we combine like terms, is simply x, like we wanted. When we do the composition both ways, f of g, g of x, both ways, the answer is x. That means, yes, these two functions are inverse functions. One undoes the other. That is an inverse function, which we write with the notation f inverse with a little -1. Looks like an exponent. It's not an exponent of x.